Aloha, everybody. This is the second video of improper integrals. And here we will do more examples of proper integrals and talk about the comparison test. All right, so let's get started. Suppose you have the integral from 1 to infinity of e to the negative x dx. And if you look at the integral, the problem is infinity, right? So we can't exactly take the integral up to infinity, but what we can do is, let's say we can take the integral up to some point b, and then let b approaches infinity so that we can get a very, very good estimate for that integral, okay? And that if the limit exists, okay? So the antiderivative of e to the negative x is negative e to the negative x, and we are going to evaluate that from 1 to b. And then negative exponent is the reciprocal of positive exponents, and that's what you have. So when b goes to infinity, then you would see a very big number on the denominator here, right? And 1 divided by a really big number is going to go to 0. So the integral will converge to this value right here, and that is 1. All right, next, the integral from 0 to 1 of ln x. And if you look at the graph, the problem is at 0, right? Because that's the asymptote there. Okay, so what we can do is not to take the integral from 0 to 1, but take the integral from a to 1, then let a approaches 0 from the right, because that's the interval that we are talking about. So a is approaching 0 from the right. Okay, now integral of ln x dx is going to require a integration by part problem. Okay, so let u be ln x, dv be dx. Then du is 1 over x dx, and v is x. The integral of dx is just x, right? So then you'll have u times v minus integral of v du. That's how it works. And you will have the integral of ln x is ln of x ln x minus x plus c. Now we are going to evaluate that from a to 1, and then we're going to take the limit as a goes to 0 from the right. Okay, so ln of 1 is going to be 0. 0 times anything is 0, so these are zeros. So what we have left with is -1. So the integral converges to -1. That's awesome. All right. The integral from 0 to pi over 2 of tangent x. Now, if you think about the curve tangent x, the asymptotes are where all the pi over 2 multiple of pi over 2, right? So then we would say, no, we cannot take the integral up to pi over 2, but what we can do is take the integral from 0 to b, and then let b approach pi over 2 from the left. Okay, so tangent x dx, tangent is sine over cosine. So if we do a little u substitution, u is cosine x, then du is negative sine x dx. So this integral basically is just the integral of -1 over u du, which is negative ln of absolute value of u plus c, right? So we are going to use that and evaluate from 0 to b. So put the u back in, you have ln, negative ln of cosine of x. Okay, well, let's deal, which one are we going to deal with first? Well, I know cosine of 0. Cosine of 0 is 1, so I will have ln of 1, and that is going to go to 0. The other one, when b is approaching pi over 2 from the left, then cosine of b is approaching 0. So think about where ln of 0 is going to go. ln of 0 is going to be approaching negative infinity. So negative ln of 0 is going to be approaching infinity, and that isn't going to work. So we say the integral of tangent x dx from 0 to pi over 2 diverges, does not go to a certain value. Okay. Comparison tests is very helpful when we are dealing with improper integrals. Okay, so let's visualize that. And as you stare at the screen, you see there is purple and green, right? So purple is a S of X, purple is L of X, and I would say that would be the larger function value. And then S of X is the smaller function. So let's visualize that right here. Okay, so suppose S of X is a positive function with positive values, and it is less than or equal to L of X. Okay, so that's why I call it S and L, S for small, L for large, right? So what is this comparison test telling us? It's telling us that if the integral, the improper integral of the larger function, purple, if that converges, then S, the integral of S of X dx, is going to converge as well. Logically makes sense, right? If the bigger integral goes to some number, let's say it converges to the integral from a to infinity of L of X dx, if it converges to some number, whatever that number is, then the smaller function here is going to have to follow suit because it's being guided by the larger number, right? Not necessarily converge to the same number, but it is going to converge as well, okay? And then what happened then? Well, how do we test for divergence? Well, if the small one diverge, then obviously the big one is gonna even get bigger. So it's going to diverge as well. Okay, so that's what the comparison test says. Now, how do we use it? Well, given the fact that we know that this right here diverges, okay, and you'll talk about the 1 over p power, the integral of 1 over p power. If p is less than or equal to 1, then it diverges, okay? So we know for a fact that this one diverges. Now, how are we going to use that to show that this one right here is either going to converge or diverge? Well, the comparison test said if this thing diverges, and let's say if this is going to be bigger, right? So suppose that this right here, we're hoping that we're going to have to show that the second integral or the second function is larger. Okay, so the one that is diverging that we know must be the small one, and this must be the larger one, right? The larger function. Okay, so what is our job to do? Our job is to show that S of X is going to be less than or equal to L of X, like this, okay? And the function values are positive. Okay, so make sure that the function value are positive. So how do we know that that's positive? Well, square root of x squared is a positive number. X squared is greater than 1. So x squared minus 0.5 is going to still be a positive number. And then cube root of a positive number is still going to be a positive number. So both of them are positive. Now our job is to show that this one right here, the one that we know, is smaller than the other. Okay, so how do we do that? We can establish this relationship here. X squared is going to have to be greater than x squared take away 0.5, right? Because x squared is a positive number. Okay, so then cube root of both sides, that inequality still holds. And then what happened when you take the reciprocal of that? Okay, so if you have, say, 3 is greater than 2, well, what happened when you take the reciprocal? What's the relationship between 1/3 and 1/2? That right there gets switched, yeah? So the function in green is smaller than our function in purple, which is what we want to show, right? So we have this condition met. One of them is smaller than the other one. The smaller the integral, the integral of the smaller function diverges, so that the integral of the larger function gonna have to diverge as well. And that is how the comparison test work for improper integrals. And that is how we deal with all of these continuities. And that is why you have learned continuities in Calc 1, right? That's one of the reasons why. And that is it for this lesson.